The technical problem was to keep the neutrons inside a mass of uranium and not to escape before they caused fission. And the question was, as it was for the Germans, how big does that mass of uranium need to be? If it got to be too big, it would be impossible to produce in the course of the war. If it was tons, as Heisenberg at first suspected, if it was small enough, it might actually form a bomb that could be delivered by airplane. It was important to distinguish, as the scientists in the United States quickly realized, between the fast processes, these prompt fissioning neutrons that went from one knocking a part of a nucleus to another, and the slow neutrons, or the delayed neutrons, that were involved in making just a reactor. The basic problem of making a bomb fell into two parts. At first, as in the German case, the American scientists thought that their only path forward was to take uranium, over 99% of which is uranium-238, that is to say, protons plus neutrons equals 238, and to extract that 0.7% of naturally occurring uranium that was a lighter form of uranium that only had 235 protons and neutrons. And if you could isolate this fissionable piece, that in sufficient quantity, you could make a bomb from it. The problem is that these two different forms of uranium act chemically exactly the same way, so no chemist can help you. The only way to separate them involved something physical that would separate a light form of this element from a heavy form. It's a very difficult task. But once you have the uranium-235, it becomes all too easy, all too tragically easy, to assemble it into a nuclear weapon. The other possibility was to design a weapon using plutonium-239. Now, plutonium is a substance which has a very long half-life compared to our lives. It's 24,000 years before half of it decays. But 24,000 years is as nothing compared to the age of the Earth, so there's none of it around from several billion years ago. That means you have to make it. Making it is difficult, and you need a reactor to do it. But once you make it inside the rods of uranium by bombarding them with neutrons, then it's easy to separate. That is to say, chemists can help. You can dissolve it in acid and separate out the plutonium, which is chemically different from the uranium. It's an exceedingly toxic substance. It requires a reactor to produce it. But once you have the plutonium-39, one additional problem arises, which is it's very hard to assemble quickly enough to detonate before little pieces of it begin to detonate and blow itself apart before it becomes a very consequential weapon. The process of making plutonium itself comes in stages, and at the fundamental level, what happens is you have a uranium nucleus, a neutron comes and gloms onto it. The neutron then decays into a proton and an electron. The electron flies away, and another particle, which we now know is the neutrino, flies away. And now with an added proton, the uranium is actually not uranium anymore. It's risen one stop on the periodic table and become neptunium. And neptunium can then get another proton and become plutonium. So it's a two-step process. You have to bombard these uranium rods with lots of neutrons, making some fraction of the uranium into neptunium and some neptunium into plutonium. But let's go back to this problem of separating the two kinds of uranium. You have to do it physically because, as I mentioned, chemists can't help you. It's the same stuff. It's the same element. One possibility is to heat it up, and the lighter atoms will get going faster than the heavier atoms. You can use that to separate the light from the heavy. Another possibility is to put it under pressure, and the lighter ones will make their way quickly through some sort of porous medium, and you can use that to get a higher ratio of the light stuff compared to the heavy stuff. Or you could send it around a kind of a racetrack using magnets to keep it in the circle, and then the lighter ones would fly off more quickly, and you can separate the heavy from the light in that way. Three different methods. All were prosecuted to one degree or another in the war. All have been prosecuted to one degree or another after the war. We begin with uranium mining. It's a difficult, dangerous problem. It was what Einstein was worried about because for a while the United States didn't think it had very much uranium. In fact, it has enormous amounts of uranium. Canada, as Einstein knew, had a lot. The Belgian Congo had a lot. Uranium actually turns out to be pretty common. Then you take that uranium ore, you use acid and various things to extract, you crush it, and you get out this stuff called yellow cake, a uranium oxide, and then you take that and you mix it with another substance and you keep going, and eventually you get a gas called uranium hexafluoride, and that gas can then be used to do these various processes, to heat it up and use temperature changes to get out the lighter stuff, or you can spin it around really fast like a centrifuge, the way you separate out the heavy and light parts of blood, for example, or you can use this racetrack technique that I described earlier. So uranium hexafluoride it's a corrosive, difficult material. There's lots of it around. It's actually formed a big part of nuclear waste, which we'll talk about later. You can see here the size of the plants that are involved. You have the gaseous diffusion plant at Oak Ridge, Tennessee. It's one of the biggest industrial plants ever made. You have the thermal plants. They're also gigantic. You have these electromagnetic separation facilities. They're also a big operation. In fact, they ended up using so much of the silver supply of the United States to run their magnets that the government was forced to issue steel nickels. If you've ever seen a steel nickel from the war years, it's because of the atomic bomb. All of these processes combined to produce enormous effort that ended up costing about $2 billion and ran from 1942 to 1945. In 1945, the first of these weapons was tested, and the uranium bomb was considered so incredibly straightforward that it was never tested, that there seemed to be no reason to test a bomb. The first uranium bomb that ever exploded in the history of the world was the one over Hiroshima. The bomb that was used over Nagasaki was rather different. This was a complicated problem. You had to get the plutonium to come in very fast into and compress it from a sort of grapefruit size to a golf ball size. And that was a tremendously difficult problem that took very great calculations and some of the work of both the earliest computers and some of the great mathematical physicists, applied mathematicians that the world had to offer. So that was the one that was tested. And here I think it's worth seeing a clip of a wonderful documentary film by John Else as he describes that moment, as he talks to the people who were there for that first detonation of a Nagasaki-type plutonium bomb.
Memo, 11 July, 1700 hours. Both charges completely papered. Work another night shift if necessary to complete this job. Request personnel as necessary. Memo, 12 July, 1600 hours. Seal all holes in case. Wrap with Scotch wrap. Box charges, inner and outer with 2 spares for each. Memo, 13 July, 1300 hours. Assembly starts. Remove polar cap and dummy plug. Gadget now belongs to tamper people. G engineers work until 1600 with active material insertion. Dummy plug hole is covered with a clean cloth and explosives people take over. Insert HE. This is to be done as slowly as the G engineers wish. Remove all chains. Clear the deck.
Well, I expected that what they were working on, they were going to try.
July, 0800 hours. Rig guidelines, lift to tower top. Ready for X unit at 0900. Bring up G engineer's footstool. 14 July, 0900 hours. Wiring of the X unit proceeds under the direction of the explosives people. Tower platform should be tested with concrete weight as per Oppenheimer. Detonators placed to conform with requirements of informer switches. HE people stand by to criticize potential rough handling. Note that once detonators are on sphere, no live electrical connection can be brought to the X unit, informer unit, or anywhere else on the sphere. All testing must be done before sphere is lifted to tower. After that, it is too late. 14 July, 1700 hours. Gadget complete. Should we have the chaplain here? The betting pool cost $1. Edward Teller bet on a blast equal to 45,000 tons of TNT. Oppenheimer bet low, 3,000 tons. And I. Robbie put his money on 20 kilotons. Young technicians were horrified to overhear Enrico Fermi taking side bets on the possibility of incinerating the state of New Mexico.
The test was set at midnight. The prediction was there'd be 60-mile visibility and a certain wind pattern. Well, at midnight, it was raining cats and dogs, lightning and thunder. Really scared about this object there in the tower. It'd be set off accidentally. So you can imagine the strain on Oppenheimer, on Robert Oppenheimer, this.
I remember it was one of my memories of that time having to go up the tower to turn on a piece of equipment. So I was one of the last, not the last person by any means, but one of the last people to get our equipment that was right next to the bomb, have it all turned on and tested before starting the test. And it was quite dramatic because lightning was striking all around. It was quite a fierce storm going on. In particular, one had a certain amount of respect for that atomic bomb being right next to us. Sparks seemed to be flying. Did give me a little bit of a sense of apprehension.
I think he and I were lying down right next to each other, flat in the desert, right outside the control hut at the time the bomb went off.
And we had prepared ourselves with glass, and when we could hear the countdown, when it went off, we all were looking through the glass, and then we saw what was just a tremendous, overpowering vision of this thing happening, seeing the mountains small beside it, seeing perhaps with some kind of beauty, but awesome was what I would call it, as it slowly developed, went up in the air, and made the whole desert light up as at noon and appear small. A large desert rimmed by mountains appear to be a small place. And that was just something that once that had happened, I was a different person from then on.
The legacy of making plutonium is still with us today. The sites, the reactors at Savannah River in South Carolina or of Hanford in Washington State are still enormous buildings, canyons as they're called, in which the uranium rods that have been exposed to massive numbers of neutrons are dunked into boiling nitric acid, and this horrible mess then eventually dissolves the rods. Those are filtered out into the plutonium separated and eventually assembled into the plutonium bombs that formed part of the arsenal. What I'd like to do next is to think in a slightly orthogonal or unusual way about what happened to these bombs as they were let loose over Japan, and to take as an example not just the pictures, which I think many of you will have seen of the detonations over Nagasaki and Hiroshima and some of the legacy of destruction that they left, but also some testimony from some of the people who were there. And for that, I'd like to have join me in conversation Hilary Shute, who is one of the best scholars at work today on the graphic novel and the way it was used by one of the people who was born in Hiroshima and who used his writing and drawing over the course of a lifetime to try to understand what had happened there.